starting after the break, not redoing anything, of course. Let's talk about calculus on M. So I'll draw this picture here. So here's U, and here's V, and here's a picture of my surface, M. All right. And so if you fix a point, so what I'm going to try to do here is describe the tangent space to M, and also how we're going to differentiate functions on M in terms of, and how the patches come into play with that. So if we pick a particular point here, all right, U naught, V naught, then we can look at this vertical line, right? And so that vertical line is parametrized by what? Basically, U equals to U naught, V equals to V, right? That's that vertical line. And the horizontal line, what I do? Is it not, you cannot see it? And this one would be, you know, V equals to V naught, U equals to U, right? Because U varies as we go along that line, right? Now, the patch, right, takes us and does, the patch goes from here to there, right? Takes us from R2, the parameter space, over to the surface M. And so if you think about it, over here, it's going to take that vertical line and maybe map it to something that's a curve over here, right? And it's going to map the horizontal line to also something that's like a curve over here, right? And in particular, I could say that, you know, the yellow one is alpha. Alpha is parameterized by V, so like alpha of V would be x of what? U naught V, right? And, whoa. Then the beta, the orange one, is parameterized by U, so I could be like beta of U is x, allow U to vary, freeze V naught, right? And so these are just like natural coordinate curves, right? And you could repeat this story for a whole grid of lines, right? And you'd get a curved grid over here. And that's basically the idea of the patch. But we can also talk about the derivatives, right? The tangents, if you will. So what's the tangent to, what's alpha prime? Alpha prime of V naught would be like this, right? And on the flip side, oh, whoa, oh, goodness. This one, beta prime of U naught, right? And I'd like to say that those vectors that I just drew, those are in the tangent space to the manifold, surface, at the point in question. Let's call this point P. All right? So let me be more clear here. So definition, actually. The tangent space to P of M is going to be the set of all, I'll just use words, is set of vectors tangent to curves which pass through P. And that's not quite good enough, because I'm not just talking about any old set of curves in R3. What kind of curves am I talking about? I'm talking about curves that are on the surface, right? Curves that are on the surface. Curves on M, which pass through P. All right? And if I think about the collection of all tangent vectors to those, that's what I would call the tangent space to P at M. Excuse me, tangent space to M at P. So, you know, if this is the point in question, you can think about, you know, there's how many different curves are there that go through that point. There's like no shortage of them, right? Whatever. And if you start thinking about all the possible tangent vectors, you can see that they form a what? They form a, well, not a patch, but the tangent space, which we could geometrically, it's horrible, we could geometrically identify with the plane, right, which just kisses the surface at that point, and it's just, you know, has all the possible tangential directions to curves. What's a basis for that tangent space? So yeah, these, by the way, I should mention this is actually has a special name. This is partial x, partial u at u naught v naught. This guy is partial x, partial v at u naught v naught. Right? In other words, this is x of v, and this is x sub u at the point u naught v naught. X sub u points in the direction of increasing u. X sub v points in the direction of increasing v. All right? Now, here's a theorem. Tangent space to P at M is equal to the span of x sub u at u naught v naught, x sub v at u naught v naught. Oh, I really get tired of writing that point dependence, but you know, here where P is equal to x of u naught v naught, and x is patch, all right? Patch at P. I should say patch near P. I'll just say at P, but understand when I say it's a patch at P, I mean that the patch covers the point P and points nearby it, all right? That's a theorem. How do we prove that theorem? All right, so proof. So I think, you know, Neil, he has segmented the proof. He has like a lemma before and some other things. I'm just going to put it all together and kind of just try to discuss it organically here. So the idea is that to describe a tangent vector, we have to look at sort of an arbitrary curve on the surface, right? And understand what the derivative to that curve looks like. So a little bit sneaky what goes on here, but we start with the surface, right? And we're going to assume that, you know, there's a patch. X of d covers the point in question, all right? And so back over here, we've got our v, we've got our u, all right? And we've got some kind of domain D, X maps from there to there. This is what we have to work with. All arguments about surfaces from this differential geometric perspective have to be run through this patch construction, pretty much. Or that alternate viewpoint. All right, we'll get back to that eventually. So we got to think about an arbitrary curve through the point P and study the tangent to that arbitrary curve, right? Like this. So let's call that curve alpha. right? Now here's the sneaky part. If you have a curve alpha, which is, say, parameterized by time t, right? So like, and without loss of generality, we're going to assume that alpha of 0 is equal to p, and the alpha has a domain like, which includes 0, and alpha is a mapping to M, which is a subset of R3, right? Great. But the thing is, the patch is invertible, right? So we can track back that curve to a corresponding curve over here in R2, right? Like there is something that came from over here, like so, right? And so this one, we'll call a typical point here, A1 of t, A2 of t, all right? So in other words, we'll let the x inverse of alpha, x inverse composed with alpha will be A1, A2. Now that is naturally a mapping from I to R2. Specifically, it's a mapping to D, which is a subset of R2, where the parameters of the patch that we're looking at line up. Whoa. Oh, yeah. Sorry, I was looking at something like, what's that? Never mind. Come on. So, I mean, what I'm blathering on about right now is actually his lemma 3.1. If you want to, check up on me. Oh man. All right. So let's see here. What do we have? We have alpha of t is equal to x of a1 of t, a2 of t, right? And our goal is to describe what alpha prime of 0 is. Alpha prime of 0 is a tangent vector to the point P here, and we'd like to describe what alpha prime of 0 looks like, all right? My goal is to prove the theorem, which says that it's a span of the u and v partial derivatives, all right? So, okay. Great. So alpha prime of, what's alpha prime of t equal to then? ddt of this, right? Now, to be more explicit, see, I don't know if being more explicit helps or not, but I mean, technically, you could think about x as being equal to like x, y, z. I have that sort of thing written in my notes. I'm not sure that really helps, but I mean, we can do that. So it's really, x of a1, a2, comma y of a1, a2, comma z of a1, a2, all right? But here, the x, the y, and the z, these are functions of u and v, right? I mean, that's the notation here. So when I take this derivative, I have to do the chain rule. And the chain rule here, well, I have to do chain rule 3 times, actually. Once for x, once for y, once for z, like so. And so for each one of these, I have to do the chain rule. And the chain rule here is the following. It's partial little x partial u dA1 dt plus partial little x partial v dA2 dt, comma, the same with x replaced with y, and then again with x replaced with z. Question? So, I mean, this is like x of uv, but here u is a1 and v is a2, so that's why the chain rule looks like this. But the a1 and a2 are also functions of time t, so this is the chain rule. So then I have partial y, partial u, dA1 dt, plus partial y, partial v, dA2 dt, partial z, partial u, dA1 dt, plus partial z, partial v, dA2 dt. Right? Oops, let me erase that. Just about the time I get all these pictures erased, I'm going to need one of them. So what do we got? Can you guys see how to... If you look at this, though, you notice what happened? We have this common, this guy, this guy, this guy, right? We've got a common dA1 dt we could factor out of those 3 terms. And we have a common, what? dA2 dt, which we could see there, there, and there, right? So factor this out. What do you got? We have partial x partial u, partial y partial u, partial z partial u, dA1 dt, plus partial x partial v, partial y partial v, partial z partial v, dA2 dt. In other words, what we have is we have partial x partial u times dA1 dt plus partial x, big X, partial v, dA2 dt. Now this derivative I did is good at arbitrary time t, you know, inside the domain as appropriately limited to the domain of alpha and such that the patch makes sense. But what happens when you plug in t equal to 0 into this thing we just did? We got alpha prime of 0 is what? X sub u of what? When you actually plug it in, it's x sub u of alpha of 0, you know, dA1 dt at time 0, plus x sub v of alpha of 0 times dA2 dt at time 0. Which is to say that the vector is in the span of the partial velocities, right? See that? Remember alpha of 0 is p. this is P. So in other words, alpha prime of 0 is an element of the span of XU. I shouldn't say alpha, I'm sorry, I shouldn't say X sub U of alpha of 0. What should I say? X sub U of, oh, good grief. It's supposed to be U naught V naught. And what is this U naught V naught? Where X of U naught V naught is equal to that point P, whatever that point P was. So if you're keeping track, so I've been following roughly bits and pieces of my handwritten lecture 12. So I wrote these sort of pretty marker note things, and there's PDFs of these posted on my website if you ever want to look at them. They're more or less just me working through O'Neill, so you don't really have to look at them. But if you're wondering, what I'm looking at, it's that. They are posted. But as tempting as it is to say everything that's on these pages, it's probably wise to not say all of it. All right? So, okay, so what do we have? The tangent space to P, what's it look like? It's the span of the partial velocities of the parameterization, right? This is what we should have learned in Calculus 3 as well, right? Then you take the cross product of these, and it gives you a vector which is perpendicular. We call it the normal vector field. Remember that? So, any questions about this? Let's see here. It's probably healthy for me to write a little bit more in terms of calculation-wise. Here, notice we mark X sub U. You could also write as partial U of well, you could write it this way. It's X U1 plus Y U2 plus Z U3, using U1, U2, and U3, the usual Cartesian basis like we did before. So we'd like to also look at the tangent space to the surface as a differential operator. And so getting back to that world of happy notation, another way you could see this would be that's really just partial x, little partial x partial u u1 plus little partial y partial u u2 plus little partial z partial u u3. Okay, great. And I actually prefer the notation, guys. Little x u u1 plus little y u u2 plus little z u u3. But of course, what's the other notation you could use here? If this, yes, please give me another notation that would make my day complete, right? But sometimes we use this as well, right? So likewise, can I say this? Yeah, that's fine. There's something else I want to say here, and I can't quite put my finger on it. X of v, on the other hand, would be xv, yv, zv, right? All right. Now, I guess technically my proof is not quite complete. Similar to our discussion earlier, Audric, I've only shown half of what I really need to show, you know? Because the calculation I've so far done really just shows what? That well, I don't know. Maybe it actually completes it. I don't know. I mean, I took an arbitrary curve and I showed that it was in the span. I guess I should also, I mean, for completeness, I guess I should provide a curve which takes these vectors. Does that make sense? As their tangents. That's what I do in the notes anyway, on page 13 of my handwritten lecture, lecture 12, I believe. So I'm just like, well, sorry. Something's bothering me. Oh, okay. Right. So I think what I've shown at the, I understand. It's the same thing we were fighting earlier today, Audric. Okay. So what we have just shown is that TP is a subset of the span, right? Exactly. So we also would like to take an arbitrary thing in the span and show that it's in there, right? So what's an arbitrary thing in the span? So what's an arbitrary thing in the span? Well, Ooh. Right, let's see, right? I'm running out of letters here. I need another letter. Let's say W. So W equals to like C1 XU of U naught V naught plus C2 XV, right, of U naught V naught. That would be an arbitrary thing in the span. So how do I show that that is in the tangent space with our current understanding of tangent space? I need to construct a curve, right, which goes through the point P at time 0 and takes that as its tangent vector, right? So what I do then is I say alpha, I say let alpha of t equal to x of what? Now here's the sneaky part. X of, well, oh goodness gracious, U naught comma V naught plus T times W. Does that make sense? I don't know if that actually makes sense yet. Oh, I'm an idiot. That's not what I do. I'm a dummy. Well, it shouldn't be W itself that I use. It should be T times what? What did this calculation kind of reveal? That we pick up like dA d1 dt times dA2 dt. So thinking that kind of backwards, we should put C1, C2 here. Instead of W, right? W wouldn't even make sense. Because W is a vector in 3 dimensions, whereas we need a vector in 2 dimensions because we're working in the domain. We're feeding it to X, which takes in vectors in R2. So, in other words, this is serving as the sort of A1 of t, A2 of t, all right? We let that essentially be the A1 t, A2 of t. And then we've actually already done the calculation in the previous derivation that shows that alpha prime of t is what? Right, it's like basically partial x, partial u times dA1 dt, right? Plus partial x, partial v, dA2 dt, suppressing some notation here for a bit. But dA1 dt and dA2 dt are exactly C1 and C2, you know? And so what do you got? You got W. Well, when you plug in times 0, then that makes this at U naught V naught. Sorry, if you write all the dependents here, it'd drive you nuts. And so this path is the one for which we differentiate and we get back W. It's not the only one, but it's one that will do it. So now we've shown that the span of XU, XV is a subset of TPM, and since we have double containment, they're equal. Now the theorem's finally complete. Although I think this theorem and discussion is also useful because I could say a little bit more. Like this actually shows me how to push forward things through the patch. We can talk about pushing forward things through the patch. All right, so let me just say that while we're here. Push forwards. So just here's a picture, you know. Here's our UV space, right? And then here's our surface. And so you can think about, you know, if I have C1, essentially if I have C1, C2 over here, you know, attached to the point U naught, V naught, then if I look at the push forward under X of that, what happens? I get a vector over here at the point P. I get X push forward of C1, C2. And what is that vector? What is that actual push forward vector? Yeah, the push forward of the tangent vector C1, C2 it's actually, C1 partial x partial u plus C2 partial x partial v. I can be a little bit more basic. That's a pun. Sorry. So the push forward of 1, 0 is partial x partial u, whereas the push forward of 0, 1 is partial x partial v. Now, admittedly, I have yet to define push forward. I'm just telling you some things that are true about it, right? I don't think I've defined push forward in this context yet. I defined push forward for like maps of functions from Rm to Rn, right? And actually that same definition works here. But, I'm not sure that's actually the definition O'Neill gives. That's why I'm a little bit worried. But, I mean, that's essentially what happens is you take the unit vector in the in the u direction here, and it pushes it over to a unit vector in the partial u direction, and just like that. Okay, so let's talk about the other viewpoint for a second here. Other viewpoint. So we've got M equal to XYZ such that G of XYZ equals to what? Some constant, right? It's a level surface. How do we understand curves in that context? Like, what's the natural way to talk about things in that world? So here, if you had a curve, right? Alpha, right? What does it mean to say that that curve is on the surface? How do you judge that? See, in the discussion, the theorem we just proved, as guided by lemma 3.1, we kind of had to go, well, that means that there's a path back in the parameter space that maps through the patch up onto the surface, and then we can study calculus through that, right?
Can't we say that the set that spans that curve is within the surface set?
This set, do you mean this?
Well, if we had the equation to the curve,
Mm-hmm.
we would know the range and domain of the curve.
Uh-huh.
What's to say that if you had those, could you say that the domain is contained within the surface?
Yeah, so you want the image of the curve to fall on M, right? Mm-hmm. And how do we judge that? We judge that by whether, if we could plug the equations for if you had the parametric equations for alpha, right, you could plug them into the corresponding level surface equation, and if they work, then it's on the surface, right? But a simple and elegant way to say that is that G of alpha of t is equal to C, right? Now notice here that this G is a function, right, from R3 to R, right? Alpha, in contrast, is a function from some subset of the reals to R3, right? So you can compose them, and that means we can differentiate this, right? And what happens when you differentiate this?
You get 0.
Well, yeah, you get 0 on that side, right? But what do we get on the left-hand side? Derivative of a composite, right? So
Yeah, you have G times
yeah, we get a gradient of G at alpha of t dotted with d alpha dt. That's the chain rule here. But on the flip side of things, that's equal to 0. So what's that show you?
it is on the surface.
Let's see here. So if, let's say, if alpha of 0 is equal to p, all right, as we often talk about, then alpha prime of 0 is perpendicular to the gradient of g at p, right?
And the dot product would be 0.
Yeah, the dot product 0, which is to say that the curve has to be perpendicular to the gradient vector, right? That mean, and this is an arbitrary tangent vector also, right? So this goes to show us that the tangent space to P at M is, perpendicular to the span of the gradient vector of G at P, right? But then we have to think about dimension, right? There's 3 dimensions that we're working in. So we can see from this that the tangent space to P at M, the perp to that, is nothing more than the span of the gradient of G at the point P, right? And that, of course, is the normal space to P at M. So if we want to find the normal space to P for a level surface, we just calculate the gradient, plug in the point. Got it. So let's see here. For example, just try to bring it back down to earth here for a second. Suppose we had g of x, y, z equal to, I don't know, x, y, z equal to 8, right? I want us to find the tangent space and the normal space to this surface at the point 2 minus 2, 2. Oh, excuse me, 2 minus 2 minus 2. let me put that. Let P equal to 2 minus 2 minus 2. All right? That has G of P equal to 8, right? So P is an element of M. It's a point on the surface that I'm interested in here. Can you tell me what is the tangent space? And what's the normal space to that look like? Well, let's see here. Gradient of G is yz, xz, xy. So the gradient of G at the point P, which is 2 minus 2 minus 2, is what? Bless you. Wait a minute, do we bless yawns? No? What's proper Alabama etiquette for a yawn? What am I supposed to do? I'm a northerner, I don't really know.
Get a ruler and smack.
Just get a ruler and smack them? Should I throw chalk at them?
If they're left-handed, you can just beat them.
Such violence. All right.
My dad was coming through school. That actually happened.
Oh, yeah?
Yeah.
Let's see here. 4 minus 4 minus, so there you go. 4 minus 4 minus 4. That is a normal vector to the surface, right? Great. What's the tangent space? So we are going to be lazy. We are going to guess the vectors which are perpendicular to this vector. I will start 0, 1, minus 1, you can easily check that that vector is perpendicular, right? The dot product of those two is 0, right? Now, how do we find the third vector? You got two choices. You got two flavor choices. The one is, and I don't recommend this unless you just really are itching to calculate a cross product, you could take the cross product of these two. That would give you a perpendicular vector over here, right? If you took the cross product of these two, you could do that. But I like to try to guess. So I'm going to start out with like a 1 here. Right? And then, since I can't quite see it in my mind, I'll put AB there just to work it out. So what do I need? I need 4 minus 4A minus 4B equal to 0, because the dot product of this and that is this. So what should I make A and B equal to? I mean, you got many choices. Any one will do. Like, how about we could make A equal to 1 and B equal to 0. There you go. Are these linearly independent? Yeah. Right? Now, do we have a calculational method to find the tangent space here? What would you do if you wanted to be more systematic and you didn't feel like guessing? What did we learn we could do? Well, yeah, we could do the cross product. That's one way, and that would be superior to my answer in the sense that it would have given us a orthogonal basis, which would have been nice. But the method that I've tried to share with you guys is that we could look at the null space of 4 minus 4 minus 4, right? And you could try to find a basis for that. So, or you could just use 1 minus 1 minus 1, since 4s are annoying, right? Divide by 4. So you'd be looking at x1 minus x2 minus x3 equal to 0, which would give you x equal to x2 plus x3, x2, x3. So you could use x2 times 1, 1, 0, plus x3 times 0, times 1, 0, 1. And I think you can see that these two vectors are also perpendicular to that guy. Yep. So there's another way we could find the tangent space here after we understand it's normal to the normal space, right? Okay. Now, so getting back to our patch discussion, how would we find the normal space in this viewpoint? So over here, we would find the normal space to P at M as the span of XU at U naught V naught cross XV at U naught V naught, right? This is the cross product, right? And in fact, I should make a definition. This is actually kind of an important definition for the bigger scheme of things in here, which is if we have a patch, right, we can look at something called the normal vector field, right? So definition. Actually, I got a couple definitions. A tangent vector, given given surface M, number one, an assignment P maps to, let's say, V of P, an element of TPM for each P and M. Well, it doesn't have to be for each P and M. That's too strong. Well, that's what it says. Fine. For each P and M is a tangent vector field. Tangent vector field to M. 2, an assignment P maps to VP in the perp to M, the tangent space of P at M for each P, is a normal vector field. To M. All right. So we've got a surface, right? We know a bunch of ways to construct them. And now we know what the tangent space looks like. It's a span of the partial velocities, right? And we can talk about vector fields, which are tangent. So some example. So an example of one would be like if I have a patch, right? I could do something like V of P equals to golly, just drawing a blank all of a sudden here. Let's see here. Let f from M to R be function, okay? So just for kicks, I want a function on the manifold. I could take a function of P times, like, partial x partial u plus some other function G times partial x partial v. So I'm going to let f and g be functions, all right? That would be a tangent vector field. Maybe not, okay. So that might not be a tangent vector field to all of them, because the patch doesn't have to cover the whole surface, right? So this could be tangent vector field to what? How about x of d, where this is a subset of M? So if you want to talk, you could replace tangent vector field to the whole of the surface with, say, tangent vector field to a part of the surface, But you see why that would be in the tangent space again? Like if you pick any point, we're looking at a linear combination of the partial velocities, right? And we proved that those are in the tangents. I mean, those are in the tangent space because of our theorem. And 2, if you look at the normal vector field defined by, partial x partial u cross partial x partial v, this is normal vector field to that x of d, right? And by the way, that's our definition. The normal vector field generated by a given patch is partial x, partial u, cross partial x, partial v, right? So. Okay. Now, see if I can erase something here. Okay, so turning the page a little bit here, I think I've skipped over a couple of things in the previous lecture, which if we need them, we'll come back to them as we hit them. But basically what I've skipped is a couple pages where I define how to talk about a function being smooth in terms of if a function on, well, let me just, fine. Curses. I can't stop myself from talking about anything. Here's M, the surface, right? And suppose you've got a function to the reals, right? What do we mean to say that that function on the manifold, is smooth? What's that mean? I said manifold, I meant surface. But so here's how we understand this function being smooth. We pick a coordinate, the patch, x of d, right? And we judge the smoothness of the function on the manifold according to the corresponding smoothness of its coordinate representative. And so what's the coordinate representative? Well, it's down here. How do you get a mapping from here to here using the x and the f? Remember that the x is invertible. I'll start you out. F composed of something. Yeah. So we're going to want a function from R2 over here to R, because f is a real valued function on the surface. Composed with x. Correct. Right, so we start here. X takes us up to there, and then f takes us back down. But if you look at f composed with x, that's a function from R2 to R. How do we judge smoothness of such a function? We already know that's calculus 3 or advanced calculus, however you want to look at it. And that's essentially the theorem. The function on the, it's either a theorem or a definition, depending on where you start, but to judge the smoothness of a function for the manifold, we just insist that the corresponding representatives are smooth. And there's a theorem that says, if you have more than one if you have more than one patch floating around, it suffices to check it on one patch. If it's smooth on one patch, I think I already told you guys if we had, we did this last time. I do remember we did this. So if we had two different patches on the surface, right, and we look